of what I will talk about. I will mention the problem of electric charge in insulators. I will then show data showing how we can obtain water with net charge. I will talk about procedures and properties of water. And finally about charge exchange between the atmosphere and solid surfaces, and the atmosphere as a charge reservoir. This topic, the problem that I want to address, was summed up past year in this short review in the American Scientist with this question: what creates static electricity? And you can read that even though it has been considered a problem of perhaps 19th century physics, it has not really been solved in many aspects, and answers are coming from other places now. Well, the same kind of statement has been repeated for a few years. I quote here two well-known authors in the area, Cass and Bailey, talking about the difficulty to make reproduce experiments, the absence of comprehensive theory, and especially the poor definition of the species responsible for charging electrostatic, for charging the electrics. And that's the last quote I will make, is by Shine. Shine is very a person that could really make such a bold statement, because he was for many years the head of research in Xerox Corporation Laboratories. And you know that Xerox is a successful company living on electrostatics. I have to say that he published this paper after he retired from Xerox. Consequences of this situation are many. Safety problems, dust explosions, fires, loss of activity in pharmaceuticals, even though many important technologies are based on electrostatic phenomena. And in nanotechnology, that becomes extremely serious, because nanoparticles, various nanobodies acquire charge that provokes powerful interactions, much greater than inertial forces. These pictures, well, the first on top is from one of the Zeppelins, the Hindenburg, but the others are from flour mills, sugar factory, polyethylene processing plant. And what they show us is that charged with flour, sugar, and polyethylene, among other solids, are powerful explosives if they acquire electrostatic charge. The relationship between water and electricity, and I will concentrate on electrostatics, was raised long ago. Of course, Faraday occupied himself on this topic. A very interesting report is by Lord Armstrong, according to which vapor is charged opposite to the water from which it is being evaporated. And indeed, in being on the surface of the earth, we should excuse me, is that a pointer? I don't find one.
It's a small cylinder. I have.
Okay, sorry. Thank you very much. This is the equation for electrochemical potential of charged species, which can be applied to define the equilibrium conditions. And it shows that if we have positive potential in a region, we should have excess cations, positive potential, excess anions, and vice versa. And since on Earth we are immersed in very powerful electrostatic field due to the condensed capacitor formed by the ionosphere and the Earth's surface, then almost everything on Earth's surface should show some excess charge. But this has been largely neglected in most cases. There are some other factors that are important. For instance, every interface, solid-liquid interface, shows ion partition, gas bubbles within water, and pure hydrocarbon tops hold negative charge. That has been subject of many papers. There is this very interesting experiment of the Kelvin dropper. And since Hygroelectricity states that every pure substance is electroneutral, many persons tend to believe that water should be electroneutral provided it is pure. But I recall we are in a natural environment or even in a non-tropic environment, always under large electric fields. And it has been shown, for instance, by Emin and colleagues, that's a group from MIT, that water collected from very different sources always carries excess negative charge. They did not discuss the reason for this. The Whiteside group also has been paying attention to this topic, and they have made some statements telling us to consider non-electroneutrality. Most of thermodynamics that we use, we consider things to be neutral, and we don't consider non-zero potential, and consequently we neglect separation due to this, except in very few areas. A few years ago, Oleg published a very provocative paper, and this was the title, Can Water Store Charge? It was criticized by Corticolucci, replied, there was a replica by Oleg, and this discussion stopped at some moment, but of course without really an agreement. In my group, we have been studying the association of charging phenomena with water adsorption or absorption. That was done in a number of papers. And I want to raise one question that has already been raised here in this conference. There is obviously a huge amount of electricity in the atmosphere. And we don't have today a model, widely accepted model, for the origin of this electricity, and of course, we are not very successful at protecting ourselves from it, and even less of using it. We entered this topic by the small end when we started using Kelvin force microscope, which is just a modification of the atomic force microscope, in which case the tip of the AFM is used as a Kelvin electrode, oscillating Kelvin electrode, that allows us to measure potential along any surface, including insulators, without contact. These are many images that were obtained from many different polymers, These are all Kelvin micrographs. The size here is between 5 and 10 microns in different images. And what the contrast in these images show is coded this way. Brighter areas are positive, darker areas are negative. So, there is one thing in common among all of them, mostly polymers, some inorganic solids. And what they have in common is that there is a pattern of potential distribution, which means a pattern of fixed charge distribution in any of these samples. To this day, I think that we have examined 150 or so samples, and that's what's always obtained. So, I will now describe the work we did to obtain water with net charge in different ways. Induced by electrified metal, either dropping through a biased needle or dropping through a grounded needle, but passing through a biased link. So, in this case, there is no contact between water and the metal. It just passes through. And here it is induced by a non-contacting insulator. And then tell you some about the properties of this electrified water. I will describe the experiment with some detail, because I think it is important to see the controls. Water is pumped through a needle using a series pump. Needle is biased or grounded, and water passes through the biased metal ring. Water drops are collected within a Faraday cup, where charge is measured and surface tension is determined by drop volume and drop profile methods. So this is done in 7 steps. Symmetrical, no flow, no bias, flow, ungrounded needle, flow, grounded needle, flow, biased needle, and the same but in reverse order. And that's what we obtain. Charge as a function of time, no flow, no bias, no charge. Water flows with no bias, small noise, that I will talk about later. When it is grounded, no charge. When we apply 1000 volts negative, then each drop brings charge to the Faraday cup. You can see the steps here until it gets here. And then we go back and charge is kept within the Faraday cup. Oh, sorry, had to change the computer, the movie will not go. But what this movie shows is how the drop shape changes with the potential applied. We start with drops, they get elongated, and at 7,000 volts, we have a stream of water, no further drops. We can measure charge per drop, depending on the applied potential, charge per volume. You see that it changes significantly. And we can also measure surface tension of the water, which decreases very much. So, charging water decreases its surface tension to a very low value, and actually, when it streams spontaneously, we can say that it gets to 0 or negative value. And that plot sums up the effect of the potential on water charge. It shows mostly negative region. The positive is essentially symmetric to this. You see that the effect increases very much as the potential increases. And that's the lower voltage region. See in more detail. You can see that that's surface tension. It's measured from the drop profiles. Measurements are very fast. So as time goes by, we can apply potential, positive, negative, positive, negative, positive, negative, and take many surface tension readings. You see that it equilibrates very fast. And it's very symmetrical, positive or negative. Now, water dropping from a grounded needle, but through a biased ring, without contacting it. As we increase potential, positive here, water drops bringing in negative charge. Here we stop applying potential, charge is kept there. Then we do a symmetric protocol for potential change, and it goes back. You see that this is very symmetric. So actually you can produce charges and you can titrate charges, positive, negative. Finally, water dropping from a grounded needle adjacent to a charged plastic sheet. Well, this is not so nice, even though we can accumulate negative charge, and when we apply positive, the plastic with a positive potential, it goes back. But this is very important because it shows you that whenever you have water, especially drops of water or aerosol, and you have insulators around, and insulators have charge, and any handling of the plastic and many ceramics will actually impart charge to them. Then water in its presence will be charged. So summing up, water is electrified by dropping from a biased metal needle. That's very highly reproducible. I did not show the data, but we measured also density and viscosity of the charged water, and they don't change. So this kind of charging I consider as a surface phenomenon, charge accumulated at the surface. So dropping from the grounded needle and so on. So how we explain this? Well, mechanism that we propose are this: when the needle is biased, water passing through, H- ions are attracted to the surface. If this is positive, they are discharged, then water flows with excess protons, and vice versa. So in this case, water comes out positive when the needle is positive. But when the needle is positive and water passes through without contacting the metal, then we don't have possibility for direct electron transfer, but we have possibility for exchange of ions to the atmosphere with the water following the electrochemical potential equation. Now I will talk about the absorption part. The problem arose when we were calibrating our Kelvin microscope. We should always calibrate and verify instruments. And calibration is done by using microscopic sample, that's 70 microns, with stripes of metal, which are interconnected with one with the next. So they are interdigitated. When we apply positive potential to one set of stripes, they become bright, as you can see in this image, and here are the grounded, or the negative set of electrodes. And that's the insulating silica. That was built on a silicon wafer. So, obtaining images, Kelvin images, with this setup, we can observe this. Running at 50% relative humidity, and we start to run here. This is scanned one line, and so on. So that's a time axis. Here, the image is very steady. We see the stripes, definitely without change. Here, everything is grounded. Here we start again to scan, but at 70% of relative humidity with positive electrode here and negative here. And then we see negative charge spreading over the silica. So somehow charge is going out of the electrodes, and that's strongly dependent on the relative humidity. Well, to cut the story short, the model that we used to explain this is here. On the silica surface, we have silicon groups, out of which H+ ions can discharge on the negative electrode, leaving behind silicate groups that are negative, fixed, and that remain in the surface until the system is short-circuited and water can come in to eliminate charge, either by oxygen release or by evaporation of water carrying excess ions. Given this experiment, we decided to do one thing, which was just to observe what happens when you have powders, solids, and change the humidity on them. Well, that was done in, for instance, in a Stubber silica sample, measuring atomic force and Kelvin image. And from these images, which give potential as a function of position, we can scan lines. And by looking at this, we observe that the electrostatic pattern in silica changes with relative humidity. The silica sample is grounded, shielded, but it is a grounded support and shielded, but you see, starting at 30%, relative humidity potential decreases, and when you go back, it increases again. So, compared to water absorption, we have negative charge. In aluminum phosphate, we have the opposite. Depending on the at higher humidity, we have more positive charge at the surface. And one thing that is, to me, is remarkable, is the size of the potential gradients that you can measure across these surfaces. Because these potential gradients can reach the megavolt per meter range. So they are very powerful, and that's something that had been previously advanced by some people as an assumption, not really as a proof. And of course, these gradients also change with relative humidity. So the model that we use is that the ions from the absorbed water, they can impart charge to surfaces, depending on chemical specific interactions or by the local potentials. When you don't apply any potential, you will depend on the chemical specific interactions. But in any case, the atmosphere is a charge reservoir for insulators. And using this, the end of last year, we published this paper showing that that's a very chemical application. We can detect acid-base sites on solid surfaces, which is very important for characterizing catalysts and adsorbents by using Kelvin force microscopy. And the only reagent to do these determinations is water, which, by the way, is amphoteric. So finally, I will mention some more metals. When you have isolated metals, to verify the Kelvin measurements that I just showed, we wanted to do direct charge measurements using Faraday cups. When we started doing the Faraday cup measurements, we observed some strange results. So went into doing control runs with the empty Faraday cups, and we observed that changing the humidity, there was also charge buildup. That you can observe here. That these are cups made with chrome-plated brass, and here relative humidity is changed, the black line, and charge, in this case negative charge, builds up. You can short circuit, repeat again, and this can go for a long time. And you can do it with many different metals, and the results are quite, they always acquire charge, but copper, for instance, acquires little charge, aluminum, a lot of negative charge, stainless steel, a lot of positive charge, and so on for other systems. So some results are collected here. As you increase humidity, chrome-plated brass becomes strongly negative, aluminum. Silicon-coated aluminum does not, remains close to zero. Evidently, or verifying the hypothesis that this is a surface phenomenon, and that's a nichrome alloy, stainless steel. So we have these different behaviors. So what we learned is that different metals can acquire positive, negative charge when you increase the humidity. And then you can make a capacitor that self-charges, which is shown here. That's capacitor made with aluminum sheets and stainless steel. And here they are short-circuited. We are measuring voltage. So humidity is uniform. So as we open circuit, the capacitor charges itself spontaneously. We are not doing anything. Here, short circuit. Again. Maximum that we managed to do were 600 cycles of charge, discharge in this way. So how it happens? So I detail here the idea. We have a cluster of water molecules impinges on a basic surface which picks up a proton, releases a negative water ion, and becomes positive, and vice versa for the aluminum surface. It's very important to recall that almost all these metals are always coated by oxide. So as conclusion, water with a steady charge is reproducibly obtained. It's a surface, and at least in these experiments we don't have any evidence for both properties change. Charge transfer is mediated by water ions, which minus H plus. Rayleigh ratio limit. Rayleigh ratio is a number that gives you the voltage at which a drop of liquid should explode, should undergo Coulomb explosion. And it's given by a limit, and we found that this can be very largely exceeded under low field. There is always a confusion in this area between field and potential. Of course, they are interdependent, but they do not work exactly the same. And also low Weber number, which is another dimensional. And this agrees with the main results that we have been collecting, according to which atmosphere is a charge reservoir for solids and liquids, and this is mediated by atmospheric water. And whenever you have absorption and desorption, you have ion partition and charging. So I acknowledge to students and postdocs that participated from this work. They were listed in the references. Acknowledge the agencies who paid for this work and for the fellowships. And this that I could not have working here, but is working in my computer, if you want to see, is the closest thing that I can, that I know to lightning within a closed environment. If someone wants to see later, we change potential, change distance, and at some point you get a number of trickling light, as in the picture that I showed of the atmospheric electricity. Just the scale is much smaller. Thank you very much.
What happens if you ground the metals? I take it you've not grounded the metals on which you see charge buildup with high humidity. What have you grounded?
If the metals are grounded, depending on the thickness of the oxide layer, you can still see a lot of potential gradients. You cannot go to very high potential, but I say very high is many volts. But I can have, I think maximum that we observed is the range of 1 volt. Because maybe, take aluminum for instance. You may have a very thin aluminum oxide layer, but that's insulator. That's a very good insulator. So actually you can build up charge on top of it, even on grounded metal.
I have a related question. See, there is a common belief that when the humidity becomes lower, there is high electricization. Like, for example, there in Russia, when in winter they begin to heat houses, and you are so much electrified that there are sparks between you and metal parts. So, doesn't it contradict? How can you explain?
Yes. Well, I thank you for asking this question because it is really essential. There is something that is not known to everyone, but you know Erwin Schrödinger, very important physicist. Schrödinger PhD thesis was exactly on this phenomenon. He was observing changes in charge dissipation from insulator surfaces and observed that as you increase conductivity, charge imparted to the surface dissipates easier. And the idea that has been around all the time is that as you increase humidity, you absorb water or absorb water, that increases the surface conductivity, which helps charge to be dissipated. And that's true. Nothing against this. It also contributes. But if you look at data comparing surface conductivity and rate of charge dissipation, right? You measure surface conductivity and rate of charge dissipation, then you see that there is something missing. And we published one paper in the Journal of Electrostatics addressing exactly this problem. It's not in this presentation, but I can resume it quickly. You take a PTFE surface. You charge it by friction, for instance, or corona, either way. And you obtain a pattern of charge. Charge is never uniform. So you can map it macroscopically and you obtain a pattern potential in different places. And you can keep scanning this surface for consecutively. You can take many scans. And then you can control the humidity. You can do it low humidity, higher humidity. What you observe is this. When you go to higher humidity, the overall surface potential decreases, both positive, negative. But there is, when you compare the changes in potential from different pixels, you see that there is no evidence of charge transfer by any surface mechanism. So in many cases, we can see a pixel with very positive potential. It decreases, is surrounded by others with negative potential, and we don't see the corresponding change in the neighbors. So, not that I dare to challenge Schrödinger, but I think that the big effect of humidity that you mentioned, which is absolutely correct, is not surface diffusion. I think it is largely exchange to the atmosphere, following the same mechanism, right? But this surely will depend on the water absorption ability of the surfaces. If you take, for instance, if you take hydrophilic surfaces, in which absorption of vapor is very fast, dissipation is very fast. And if you go to hydrophobic surfaces, where you have more stronger patterning of surface, it is very easy to observe that it's not diffusion or surface migration, it is really exchange to the surface. Actually, there are two papers. In one of them, we paid special attention to the very curious fact. Some points in a polyethylene surface would change potential much faster than others. Right? And then we went to find out why. Well, polyethylene surfaces often have oxidized spots. Right? So, to conclude, electrostatic charges are really more dangerous under low humidity than at high humidity because they last for longer. And what we should not do to build electrostatic charges. We should not expose an item to very high humidity and quickly transfer it to very low humidity. Because then you build up, you don't give time for the relaxation, and if water absorption is low, we are going to keep this charge there. And probably you have heard stories about criminals, because they are criminals, that specialize in provoking electrostatic explosions. And I think that's one of the tricks they play. See?
Okay, we're running a little late now, so if you have additional questions, you can check with the speaker at the break. We'll now stop